Hi, my name's Callum Scott. I'm from the Archaeology Department at the University of York, and today I'm going to be talking to you about human evolution. So we're going to cover several topics. Firstly, I'm going to talk to you about our ancestors and the changes that have occurred through our lineage. Next, I'm going to talk to you about stone tools and what we can find out from stone tools, how they've changed through time. And lastly, I'm going to talk to you about how we date fossils and stone tools in the archaeological record. So we've got two pictures here. The one on the left you've probably seen before. This is Darwin's interpretation of human evolution, and it's just a straight line from our ancestors to us. The image on the right is a more branching, more updated version of human evolution, and you can see here that not all of the lineages actually lead to us, and that there's some offshooting branches. So if we go right to the base of that tree, we have Ardipithecus ramidus. This is an individual who lived 4.4 million years ago. And the further back in time you go in the archaeological record, the less evidence we have for individuals. So there's only 110 specimens from this individual, so not very much evidence at all. But if we look at what we can find off of the evidence that we have, we can tell that it lived mainly in woodland, and that from the wear patterns on its teeth and the thickness of its enamel, we can tell that it had a diet which was not particularly abrasive, but may have included some hard foods. And it's consistent with a partially terrestrial diet, so terrestrial meaning living on the land, on the floor, and partially an arboreal diet, so a diet coming from within the trees. But we can tell that it mainly survived in a wooded habitat. Now, if we look at the pelvis of Ardipithecus ramidus, we can tell that mainly its pelvis resembles a modern primate, so suggesting it was really good at moving through trees and climbing. But its upper pelvis has these large repositioned gluteal muscles, so muscles in its lower pelvis, which allowed it to walk without shifting its weight from side to side, which would have saved it a lot of energy in walking upright. So this individual would have been able to climb trees, but would also have been able to walk bipedally on two legs. So here we have an individual which it still has a small brain. It's 300 to 350 cubic centimeters, so that is a measurement of the size of the brain. But it mainly also survived on an omnivorous diet, so it ate some plants, ate some meat, ate a bit more meat than chimpanzees, but not too different from what you'd expect from what we see from a modern primate, really, except from the fact that it was capable of walking bipedally. So here we have Australopithecus afarensis, the most famous individual of which is Lucy, who you can see on the right of the screen. Now, some important things to note about Lucy are that she has a lot of similarities with chimpanzees, and you can see that it's running through it on the screen here. So shoulder blades are quite similar and well suited to climbing in trees. The face is quite similar. It had long arms with curved fingers, and there are some differences with chimpanzees as well. So these differences that we see with chimpanzees are mainly seen in the spine, so the connection is beneath the skull, which allows it to walk with its head up, keeping the head steady. The pelvis is quite different. The shape of the pelvis is more rounded rather than flat, allowing it to support its body upright, and the thigh bones are a bit angled to make sure that the weight is distributed just right for walking bipedally upright. Now, some other things to know about Lucy are that she mainly derived her resources from woodlands and grasslands, which shows that she's adapted to more diverse environments than Australopithecus afarensis, and we can tell that she was consuming more plants in open environments from the isotopes that we can find in her bones and in her teeth. So at the time, the environment was shifting. It was becoming much more dry, and woodlands were breaking up, which meant that our ancestors really had to adapt to these changing climates. And Lucy, sadly, she actually met her end not in these open environments as you'd expect, where there's a greater amount of predation from hyenas and lions, but she actually there's skeletal fractures which suggest she fell out of a tree, and that's how she met her end. But she was much more adapted to a wider range of environments. She ate a wider range of foods and probably incorporated a little bit more meat into her diet in that open environment. But she still had a small brain size, so not quite what we see in our later ancestors, which are suggested to be a bit more human-like, and we'll see that in a second. So we have something quite unique with Australopithecus afarensis. We have some preserved footsteps in Laetoli. So these footsteps are about 3.6 million years old, and they show 3 individuals walking through the landscape, 2 adults and a child, and the child is actually walking in the footsteps of the larger of the 2 adults. So this creates quite a nice image of almost like a child walking in the footsteps of their dad in the snow, because the floor was covered in volcanic ash, and ash was falling from the sky as well to preserve these footsteps. But we can find out some other stuff from this evidence as well. We can see how economical their walking was, so how much energy they were saving in their walking in comparison to other modern primates. And they walked like we walk today, but with shorter legs. And another interesting thing is, unlike Ardipithecus, they have gotten rid of a large big toe on their foot for gripping trees. And the big toe is actually in line with the rest of the foot, like in modern human feet, which suggests that our ancestors actually had feet which were more like us than like apes. So the next thing I'm going to talk to you about are the finds in Olduvai Gorge, which was excavated by Mary and Lewis Leakey. And what's really interesting about this is that at the time they were excavating, it wasn't too certain whether our origins were in Africa or not, because a forgery had been produced in England to try and convince scientists that our species originated in England. Now, what's great about Olduvai Gorge is it has a natural stratigraphy, a natural cut in the landscape, so that you can get to these layers of the deep past. And actually, there's an entire African rift valley where the majority of our oldest ancestors are found because it's easiest to access them there. So at Olduvai Gorge, they started by finding loads and loads of stone tools, and these stone tools were very rudimentary and simple, and the main purpose of them was to just produce an edge which was capable of cutting, or to use a stone big enough for smashing nuts. And what we see is these tools were made by an individual called Homo habilis, and they were 2.6 to 1.6 million years old. Now, Homo habilis lived in a more open environment again. The environment kept getting drier and kept getting more open, that with less trees, and had to survive in more open grassland areas. And this meant that they had to broaden their diet to include more plants which weren't previously consumed by our ancestors. So we can see that they were able to eat some tougher foods, such as tubers and roots, which have a lot of energy in. But they didn't eat harder foods like some of our ancestors, like Paranthropus, did. They also ate more meat and probably were scavenging meat from other predators and then using stone tools to butcher the carcasses and smash open long bones in order to get at the marrow, which has a lot of energy. And they needed this energy because their brain was slightly larger. So instead of the 300cc, the 400cc that we saw with the previous ancestors, this individual had a brain size of 600, and a large brain requires a lot of energy to keep it working. But it's important to remember that at this time, our ancestors were still prey. So, for example, there's an Australopithecus africanus, which was picked up and eaten by an eagle. And we can tell this because it's still got the claw marks from when it was picked up on its skull. And here we have another individual who was eaten by a crocodile and still has the tooth marks on its foot. But there was a drastic change with the speciation of Homo erectus about 1.89 million years ago. So this species had a much larger brain. So in comparison to Homo habilis, who only had a 600cc brain, it had grown massively to 950cc. And they used this brain to produce much more complex stone tools. So Homo habilis was producing the Aldervan tools, which the only goal was to produce a cutting edge. Whereas the Acheulean tools, which Homo erectus was producing, had a much more standardized form. And you can see in the picture here that the individual who made this tool even took the care to produce the tool around a shell, presumably just because it looked nice. Now, Homo erectus, in order to have such a large brain, would have needed to produce more meat in their diet, so they needed to hunt more. They needed more energy, and they did this probably by having the first hunting. And another way to increase energy from meat is to cook it, and Homo erectus actually shows the earliest signs of having cooked food and used fire. Now, they used these abilities to actually expand out of Africa as well. So these are the earliest of our ancestors to leave Africa, and they colonized all the way to Eastern Asia. Homo erectus also shows the earliest evidence of care, so caring for another individual. We can see in the picture here, this is actually a picture of a bone which has formed a large crust around it. And now this crust is caused by hypervitaminosis, so an overdose of vitamins. And the individual probably got this from either eating a predator's liver, which has a lot of vitamin A in, or possibly it found a beehive, tasted the honey, and loved the sugar and just went crazy and ate the entire beehive, including the bee brood, and got an overdose of vitamin A that way. Now, this led to this crust forming on the outside of its bone, and it wouldn't have been able to walk or move or get its own food, yet it survived many weeks like this. Now, to survive many weeks like this, the individual would have needed to have been provided food, needed to have been provided water by another member of its group. So this is the earliest evidence of medical care for another hominin. We now move on to Neanderthals, and many of you, when you picture a Neanderthal, you probably think of a nasty, brutish individual covered in body hair, carrying a club, who you just wouldn't want to meet. It's a dangerous individual. But in actual fact, Neanderthals were probably a lot more like this. They were probably a lot more like us than we give them credit for. Now, Neanderthals evolved from those Homo erectus individuals who left Africa, and they aren't actually directly related to us. They're more like cousins to us. And they speciated around 400,000 years ago, and they survived until 40,000 years ago. And they did this because they had a very large brain, and actually their brain was larger than ours. But it was much more elongated instead of tightly bunched like ours is. So not as many connections could develop in the brain. So possibly they weren't as cognitively as intelligent as us. Now, they do actually show a lot of signs of cognitive complexity. So they do show signs of art. They do show signs of body decoration. You can see here this individual in the picture is probably not a bad representation of a Neanderthal individual. So they did use feathers for decoration. They did use ochre, and they did actually use eagle talons as decoration. They also had a much more complex stone tool technology. They used what's called the Mousterian technology, and they had this technique called the Levallois technique, where they'd hit a core and make it so that it was prepared, so that in a single strike they could take off what they needed from it, whether it was a blade or whether it was a scraper for scraping leathers, or whether it was a burin, which is used to pierce leathers. So they had a much more complex technology. Now the flip side of that is they lived in much smaller, isolated groups compared to modern humans. And when you have smaller groups, it means that you've got less individuals to help you come up with new innovative ideas. So Neanderthals probably weren't as adaptable to changing environments because they weren't able to culturally adapt, whereas modern humans were. Nevertheless, we do see signs of Neanderthal cognitive and social complexity. So, for example, on the right here, you can see that a Neanderthal has taken this stone, which had a natural hole in it, and they've jammed a bone in there, which then they've fixed in place using bits of flint, so that it produces this almost face-like image. So this is like an early form of art. On the left here, we actually have the Neanderthal hashtag, and yes, you may not believe it, but Neanderthals beat you to it. They made the first hashtag. If we compare Neanderthals to modern humans lived in much larger social groups, which allowed them to innovate much more. And we see this in the archaeological record. They produced much more complex stone tools again, which probably allowed them to produce more complex clothings, which meant that they could move into different, more harsh environments. And as you can see on the right here, they produced figurative art. And this is actually taken from a cave in Chauvet, which is 30,000 years old. And what you might not believe here is when you walk down this cave with a flickering oil lamp, like they would have done 30,000 years ago, the flicker of light picks up different images on the stone wall, and it looks like these lions are moving. So this is actually the earliest evidence of cinematography, the first movie 30,000 years ago. Now, modern humans use these technological adaptations to move into different environments, as I said, but they moved into the environments which Neanderthals lived in, and they replaced the Neanderthals. So there's been suggestions that modern humans outcompeted Neanderthals for the resources, so outcompeted Neanderthals when they were out hunting and gathering. But other suggestions say that Neanderthals lived through such a climatically variable time. There had just been an ice age and a swift change to cold climates and then warm climates again. And during that cold phase, Neanderthals lost a lot of their population. And then when modern humans moved in, modern humans had a much larger population, interbred with Neanderthals, and because Neanderthal populations were so small, they were just diluted to a level which is almost insignificant within us. So what's important to take from this is Neanderthals, they may be gone, but they still live within us. So all people of non-African descent are about 1.5 to 2.5% Neanderthal because we interbred with them, and ultimately that's why they went extinct. And if we took those genes, which are still within us, we could probably recreate the entire Neanderthal genome. So now I'm going to show you two videos. One is me in the Paleo Hub, showing you how the morphology of our ancestors' skulls, the shape of our ancestors' skulls, has changed over time. The second video is taken from the Year Centre, the York Experimental Archaeological Research Centre, and they've kindly let me video them as they do some flint knapping. So producing stone tools, and they're just going to explain to you there and show you how these stone tools are made, because it's unbelievably hard and I really struggle to even get a simple flake off them. So I'm going to show you an expert instead of myself doing that. Hi, so I'm here at the Paleo Hub. And in front of me, I have several of our ancestors' skulls, replicas of their skulls. So if I start over here with this individual, this is Ardipithecus, and we've spoken about her or him in the presentation. This individual would have been about 4.4 million years old, and it lived primarily in wooded landscapes, and it subsisted on woodland foods, although it would have been slightly more omnivorous than chimpanzees. So this individual lived primarily in trees, but has evidence which shows that it would have been able to walk bipedally, although not as well as some of the other hominins here. These next two individuals are Paranthropus. So Paranthropus are very large, robust individuals. And one thing I want you to notice here is how large the teeth are. So if we compare it to the modern human teeth, they're much larger. And they've got very, very large jaws as well, with an area here. So if you see these areas here, would have housed very large jaw muscles. And they needed this because they started to adapt to slightly more open environments and would have needed to have eaten much harder, rougher foods, which take a lot of power in the jaw and a lot of time to process and chew. And this is even more exaggerated when we look at these individuals. So if we look at the second Paranthropus skull, it started to develop a crest on the top of the skull, which would have had attached more jaw muscles. So this individual here is Australopithecus africanus, and I just want you to note how small the crania is here. And I want you to note it as well. Still got those jaw muscles though, but just note the size of the crania. And even on these larger individuals, the size of the crania is not too different as well. It's still small. When we move on to Homo habilis, this is the individual who was found at Olduvai Gorge. And these hominins, they still have that small cranium, but they're responsible for the earliest tools that we see in the archaeological record.
And it suggests that they were eating more meat, although they still mainly subsisted on plant foods, but they did eat more meat in their diet. When we get to this individual here, though, this is Homo ergaster. So Homo ergaster has a much larger cranium than the other individuals. And to survive with a much larger cranium, a much larger brain, so the cranium is where the brain is housed, they would have needed much more energy, much more food, or more energy-rich food, such as meat and fat. So this individual had a large cranium, had much more adapted stone tools, as you'll see in the presentation, and had the Acheulean hand axes, which are very standardized, uniform tools. And we'll go into a bit more about that. But one thing to note is a much more advanced sociality that we start to see with this individual. So we're going to move on to Homo heidelbergensis. So Homo heidelbergensis is a European fossil. So it's mainly associated with living in Europe. And this is actually the ancestor of Neanderthals, not ourselves. So here we have an individual who is living in Africa, and here more living in Europe. And the individual living in Africa, Homo ergaster, 1.6 million years ago, is our ancestor and responsible for our lineage, whereas Homo heidelbergensis, who was living about 500,000 years ago, although persisted until later in the record, this individual being from 300,000 years ago, is the ancestor of these individuals, Neanderthals. And one thing to note is the huge brow ridge here, and we'll get onto that in a minute. But another thing to note is just how large the cranium is as well. It's much larger than all of the previous individuals, and that suggests there was strong selection, strong natural selection for a large brain in our ancestors. And when we get to Neanderthals, we get an even larger brain size, and Neanderthals actually had a larger brain size than modern humans. But if we look at their cranium and compare it to that of a modern human, you can see that the Neanderthal cranium is much more elongated. So it extends much longer across this plane, whereas the human has a much more rounded skull. And this is thought to have a big impact on the connections in the brain that humans were able to develop, leading to a much more highly connected brain when compared to Neanderthals. And one thing that's important to note as well is those brow ridges are still maintained on Neanderthals, which suggests that they were kept for a reason. Now, brow ridges, they signal aggression, although on Neanderthals they're not as big as on Heidelbergensis. Whereas, if we look at the modern human, those brow ridges are virtually gone. And so it suggests that modern humans have adapted to show less aggression, but also have more mobile eyebrows, which are able to communicate a lot more emotion to other individuals. So one thing I want to say is Neanderthals are not necessarily inferior to modern humans. So this individual is from 56 to 47,000 years ago, found in France. And it's important to note that Neanderthals actually survived on this planet longer than modern humans. So Neanderthals survived for 500,000 years on our planet, whereas modern humans, we've only been around for 200,000 years. So it begs the question, who is the more successful species? The one that's still around today and is the sole survivor of this lineage of hominins, our ancestors, or the individual who has survived the longest.
So I have here the basic nodule of flint, and I thought we'd talk a little bit about the edge angles and how flint works when you strike it, because that's really the core of flint napping, is understanding the material properties of flint and what makes it so different to everything else. So a piece of flint like this, you have this chalky cortex and you have this grey central piece, which is where the centre of the flint material is. And when you're looking to strike a piece of flint, what we're looking at is the angle of where the stone is going to come down on and the remainder of the piece of flint. So if you picture what I've got here, if this is what we call the platform, which is the striking edge, then the remainder that's underneath it here is less than 90 degrees. And that is one of the crucial points of flint napping, is if this was wider than that, or over 90 degrees, then I wouldn't be able to use it. But because it's less than 90 degrees, this means that when I strike with a piece of stone onto here, this piece here should come away. So there, you can see, if I reconstruct it, there's the point of impact. It's quite a large heavy stone, and so it's removed quite a large piece of flint, but it's gone down exactly where I wanted it to go. And that, in essence, is the principle of flint napping, is this predictable quality of flint, which means that when you strike it at certain angles with certain force, you can predict what's going to happen afterwards. And it's only by doing that that you can start to develop the tools into more sophisticated and smaller objects. So making things like arrowheads and spearheads, or even smaller little blades. It's only by using the predictable nature of flint that you can achieve that. So now we've set up a new platform here from what was struck off. So this lip here, so if this is my platform here, this remainder here is less than 90 degrees. It will probably need a bit more force than the previous one, but we'll see what happens. There we have some of the smaller pieces that have come away. So in flint napping terms, this is called the core, and anything that comes off is a flake, and they're both useful. So the core is the piece that I'm working on, and then a flake I can pick up and modify and use as a flake tool. So now we can use this platform here to start going around and remove some of these smaller sections, and those which will come off something like this. These are useful in their own right as little knives, little blades. You could set them in a haft to use as a knife, or potentially as something like a harpoon edge. So different size stones will produce different results. So if I start to use a slightly smaller stone, it will produce less power, but I'll have more control over how I strike it, and hopefully I will have more control over the amount of flint that I remove as well. So what I'm doing now is just grinding the edge, and grinding the edge is what we call edge preparation. So when you strike the flint, you're sending a shock wave, which actually comes out as a little ripple, exactly the same as if you dropped a stone in a pond. And you're sending that shock wave through the material until it detaches at the other side, or wherever it stops. If the edge isn't strong enough to take that shock wave, it will just crumble. So one of the elements of flint napping is to prepare the edge properly, or prepare the platform properly, so that the shock wave, instead of dissipating, actually gets sent where you want it to go. So these diagnostic scars down here, this is what, if you were analysing a piece of flint, you would be able to use to work backwards to understand what's happened. So the lines here indicate a previous piece of flint that's been removed, and these are what we call step fractures, and this is where the flint has been struck here, and instead of the shockwave moving all the way down the face, it's just terminated here and left us with this little, it looks like a step. And these can keep going backwards, as you can see here, they just disappear all the way backwards. And so when we find flint tools, and you can see these markers here, this tells you something about how it was made. So that's quite a nice little backed blade. So you've got the bit of cortex there that you could hold on to, and then this would be quite useful for cutting, maybe doing some plant work or cutting some meat.
So I hope you enjoyed the videos, and I hope it gave you a bit of an appreciation for just how difficult it is to control how stones break. So if we have a look at how stone tools have changed over time, I've already said, so the Homo habilis was producing Aldebaran tools on the far left there, and then it got a bit more complex with the Acheulean producing these standardized shapes, and then in the Mousterian with Neanderthals it got even more complex again with a wider range of tools being used. So you can clearly see here on the screen how stone tools have adapted from producing just trying to produce a sharp edge, to trying to produce a shape, to trying to produce lots of different shapes which are designed for specific purposes, for specific jobs. And finally, I just want to talk to you a little bit about how we go about dating fossils and stone tools. So there's three main ways of doing it. The first one is using the stratigraphy. So the stratigraphy is how sediment, how soils and dirt have piled up over time, and we can see different dirt is piled up over different time periods. And so if we actually dig down, the oldest stuff is lower down, the younger stuff is higher up. So we can date things that way by using the stratigraphy, by seeing what layer things are in, and then judging what time period they're from that. The second way of doing it is by using the artifacts themselves. So when artifacts are quite characteristic of a time period, we can then, if we identify them at a particular archaeological site, we can suggest that that site is dated to that particular time when those tools are being produced. The final and probably the best and most reliable way of doing it is by using chemical analysis, so carbon-14 dating, uranium thorium dating, and argon dating. So this uses the isotopes of these elements to judge the date of an object. So our objects have, particularly organic objects, have a certain amount of carbon in them, and that breaks down into nitrogen over time after it's been dead and deposited. So judging by how little carbon there is left in the object and comparing it to modern bones, for example, you can have an estimate of just how old that object is. And then you can use uranium thorium dating and argon to date rock and volcanic material as well, which is really useful for coming up with how old a stratigraphic layer is, and also how old, for example, painting is as well. So uranium thorium dating has just been used to identify that a particular rock art was actually produced by Neanderthals rather than modern humans, because they dated it to a period which was before modern humans had moved into the area. So there's three different ways of dating archaeological sites, and when they all line up together, you can be very confident that what we think is the time period is the time period. So I just want to finish by thanking you all for listening, and thanking your teacher for giving me this opportunity to talk to you all. Thank you.